All right, so here we are in section 3.7 on implicit differentiation. And again, for you folks who are watching this later on YouTube, we are doing this in the live lecture today. So if anyone puts questions in the chat, I might read them on video. But yeah, so you guys who are on the live call, if you do have questions, just let me know. So for our warm up for section 3.7, we're just taking some derivatives here. We're trying to find y prime. And these get progressively more challenging here. So for the first one, y equals x squared plus 3x plus 5, that one hopefully is not too bad for us. We would use our power rule on this, and it's pretty straightforward. Y prime would be 2x plus 3, and that's it. Okay, not too bad, right? Then our next one, we shift a little something here. We just change the exponent on y. And so it's y squared equals x squared plus 3x plus 5. And right now we might not have much of a strategy for this per se, except maybe we would try to solve this for y so we could take the derivative, perhaps by square rooting both sides. You could get y equals the square root of x squared plus 3x plus 5. But notice how doing that square root there, technically it should be plus or minus, and so you end up with two different functions that you would have to take the derivative of. It can get complicated. Even if we just assume like, okay, we're just going to work with the positive part here, this might cause a domain restriction because we're working now with a radical, whereas we weren't before. Okay. And then, yeah, technically we should have plus or minus, but even just to give this a kind of simplest case scenario, that would still be x squared plus 3x plus 5 to the 1/2 power. And then we would have to use our chain rule from last section, because this is definitely an interior function and then an exterior function. So you would use one of those methods for the chain rule to find that derivative. Okay, so now we need chain rule. And we would get, I'm going to do kind of a adapted hand method here, the cover up type of thing. So I'm going to cover up the interior, and I would have 1/2 interior stuff, purple square to the 1/2 power, and then times the derivative of that interior covered up stuff. And then we would uncover the covered thing and see that it was x squared plus 3x plus 5. And so you'd put that in right here. X squared plus 3x plus 5, x squared plus 3x plus 5. Okay, to do our chain rule. So you would get 1/2 x squared plus 3x plus 5 to the 1/2 power. And then the derivative of x squared plus 3x plus 5 would be 2x plus 3. Okay. And, you know, you could write that in, oh, hey, someone in the chat made a good catch. I didn't subtract 1 from my exponent. Thank you, thank you. In doing the power rule here, we brought down the 1/2, and then I forgot to subtract 1 from the power. So this really should be -1/2. Good catch. Thank you for that. So yeah, that should be a -1/2 power on there in both cases. Let me make sure everything's all right there. So 1/2 x squared plus 3x plus 5 to the -1/2 and derivative of that inside. Okay, I think we are good there, so awesome. All right, so yeah, you could write this in some different formats, maybe putting that -1/2 exponent down into a denominator or something, but for our purposes right now, this will be sufficient. Okay. And then in the next problem, we take it up again. We add some more terms on the left-hand side of the equation. We've got y squared plus 2y plus 1 equals x squared plus 3x plus 5. So we'll try to do a little rewriting here as well. Anyone know what that left-hand side is that's on the call? Let me see if they can get it. So that we can rewrite that a little more effectively. Yeah, and someone just put it in the chat. Very good. It's y plus 1 squared. Nice. So yeah, that left-hand side is y plus 1 squared, and then equals x squared plus 3x plus 5. So we might try doing a similar thing as in number 2. Okay, you might square root both sides of this again. And again, it might cause a domain restriction of some sort. It could cause some real issues with plus or minus, but we're just trying to crank through the derivative however we can here. So we might say y plus 1 equals the square root of x squared plus 3x plus 5. And then to solve for y by itself, we could say y equals the square root of x squared plus 3x plus 5, and then minus 1, just so we can solve for y there. Then you might even want to rewrite that again and say y equals x squared plus 3x plus 5 to the 1/2 power like we did before. That way we can use our chain rule more effectively. So then when we go for that derivative, y prime would equal, doing the same type of cover-up type of thing, taking the derivative of this term would look exactly like what we just did. 1/2 x squared plus 3x plus 5 to the negative 1/2 power. Got it this time. And then times the derivative of the inside, which would be 2x plus 3. And then the derivative for this extra term on the outside there, the derivative of 1 is just 0, so that actually doesn't end up having an effect here. We would still get basically, yeah, the same thing for our derivative. Okay, so that's good. And then we come to number 4 here, which just makes a tiny change and says we're going to do y cubed plus 2y plus 1 equals x squared plus 3x plus 5. And that, I mean, if anyone can solve this for y, feel free to go for it. But this left-hand side is no longer so nice. It's not really factorable in a good form like we had in number 3 here. We can't do that anymore. So this actually becomes a very, very messy equation if we try to solve it for y. So this type of thing, we say we cannot solve explicitly for y. Okay, so explicitly is kind of a new term here, and that's not like parental guidance type stuff. This is not explicit content. Explicitly just means we can't get y by itself on one side of the equation. So y by itself on one side. Okay, that's what an explicit solution for y would be. So if this cannot be solved explicitly, we say that this is the opposite of explicit, which is implicit. So this is what we would call an implicit equation. Okay, implicit. And that is what this section focuses on here, because this is on implicit differentiation. So taking derivatives of equations like this, implicit equations that can't be solved explicitly for y. And so the big idea here for these implicit equations is that we're going to just take the derivative of everything all the way through. So we will take the derivative of everything on both sides of the equation. Okay, both sides of the equation with respect to x. Okay, or whatever variable you're trying to do things with respect to. It is x in this case. So yeah, this is the new idea there, the derivative of absolutely everything. And we kind of have been doing this a little bit behind the scenes already. When we remember that y is actually a function of x in these cases, so remember that y is a function of x. And honestly, that has come into play even in things like problem number 1, which looks very, pretty fast and quick, simple for us now, hopefully. So things like y equals x squared plus 3x plus 5, we are actually taking the derivative of everything on both sides of the equation here. It's just that one side of the equation has always happened to be y alone, solved explicitly, because we are taking the derivative with respect to x of that side of the equation of y to get the derivative overall. So we're doing derivative with respect to x on both sides of that. It's just previously it hasn't had much of an impact on the left-hand side. We just say, oh, that's dy dx. And we're like, good with it, okay? Now it's gonna get a little more complicated, but just keep that in mind. Remember that y is a function of x, like this. Okay. So we're going to use this approach on that implicit equation in number 4, the y cubed plus 2y plus 1 equals x squared plus 3x plus 5. And we're going to take the derivative of absolutely everything on both sides of the equation with respect to x. So you start out by writing your intention of what you're going to do. Derivative with respect to x of both sides. And this right-hand side of the equation really proves to not be much of a problem. Derivative with respect to x of x squared plus 3x plus 5, we're used to seeing things like that now, where our derivative with respect to matches the derivative that, or our derivative with respect to this variable matches the variable that's in the expression there. So we would just use our normal power rule. Derivative of x squared would be 2x, and then derivative of 3x is 3, derivative of 5 is 0. Okay, so we can get that right-hand side, no problem. On the left-hand side, this is going to be a little bit more of a challenge here. So let's break this up into smaller pieces, because remember our sum property for derivatives. If you're taking the derivative and you have a sum of more than one term there, you can do the derivative of each term separately. So we could take the derivative with respect to x of y cubed plus derivative with respect to x of 2y, and the derivative with respect to x of 1. And one of those is still nice. It's this one right here. The derivative with respect to x of a constant, like 1, is still 0. So that's nice. It's the other bits that give us a little bit of hassle. But here, notice that we have the derivative with respect to x of 2y. That is just a constant multiple on there. So we've got our constant multiple situation. So we could pull that 2 out, and then 2 times the derivative with respect to x of just y. Okay. So I'm just breaking things down bit by bit here. We'll leave the derivative y cubed alone for just a second. All right. And let's write this again. Derivative y cubed. We actually know what this is. The derivative with respect to x of y is just what we've been doing in a lot of our other problems. The derivative with respect to x of y is just dy dx. And so that's what we can write for that. The fact that it's just dy dx right there. Okay, so d dx of y is just dy dx. So we have 2 times dy dx. And then we don't need to write plus 0, so we can just say that equals 2x plus 3. Okay, now for the toughest part of this, the derivative with respect to x of y cubed. That part, we need to think about the fact that y is a function of x. So we are taking the derivative of y, which is a function of x, getting cubed. And so this actually becomes a little tiny chain rule that we have to do. So this is a chain rule because this y right here is not just a variable itself. We're not doing a derivative with respect to y of y cubed, otherwise that would be really nice. Y is a function of x, and we're doing a derivative with respect to x. So when those variables don't match, then you have to use this implicit chain rule type of differentiation. Okay. And so how we do this, if I'm going to use the cover-up rule, is we would see that y is the interior of this function. Okay, so if we do cover up, we basically have a purple blob interior cubed. So the derivative of that would be 3 purple blob interior squared, and then times the derivative of that purple blob interior. Okay, let me put those purple blobs right here. Blob, blob. Okay. And so let me rewrite that real quick. That way it'll make sense in the notes later. There's the y. Let me scoot these guys over just a hair. Okay. Oh, interesting. It turned those into scribbles. Okay. Here's the cover up on that y cubed thing. Okay, so we cover up the y. Okay, like so. So derivative of purple blob cubed is 3 purple blob squared times the derivative of the purple blob. Highly technical notation there. But when we uncover that and see that purple blob was in fact y, all right, purple blob is truly y. So here we get 3y squared times the derivative with respect to x of y. All right. And then those become a little more familiar expressions, 3y squared. And then we just saw what to do with this. The derivative with respect to x of y is dy dx, right there. So that's what we have for the derivative, 3y squared times dy dx. Okay, so this is all kind of side work here. Okay, side work, thinking. Okay, let me make that kind of its own little thought bubble off to the side here. Okay, and then for that derivative, finishing it up, we would go around the thought bubble, think our thoughts, and then we would have 3y squared times dy dx plus 2 times dy dx equals 2x plus 3. So I'm just rewriting this equation now, but with our derivative of y cubed in there. Okay, because yeah, if we wanted to finish solving this, we want to solve for the derivative dy dx. So, whoops, sorry, there we go. So now, solve for the derivative dy dx, dot, dot, dot. Okay, and we'll see that we can factor out a dy dx on that left-hand side. Dy dx factors out, and we're left with 3y squared plus 2. Okay, 3y squared plus 2. And that still equals 2x plus 3. And now we just divide on both sides. So we get dy dx equals 2x plus 3 over 3y squared plus 2. And that is actually the derivative dy dx in its final form. Now, you might note on this that the answer itself still has a y in there. There's still, you know, a y right here. And so that's okay. The answer for this derivative is also in an implicit form. It mixes x and y. So mixing x's and y's. Okay, and that's all right. If we had to address that, which we do in some problems, but we'll get to that when we get to that. But this is the basic idea of how to take an implicit derivative. And yes, it looks like a lot, but with practice, it will get better. You might notice here that for this derivative of y cubed, it kind of behaves like you would expect it to, going like 3y squared. That looks very much like a power rule, because it is. But then you just have to multiply by this extra factor of dy dx, because your variables didn't match. You had a derivative with respect to x of y, so you need this extra dy dx in there. So that is really what you'll see happens on a lot of these problems. It's just kind of what you would expect, and then times an extra dy dx. But yeah, that's where it all comes from. It's the chain rule behind the scenes. So a little bit crazy, but yeah, we'll go ahead and stop this here. I'll see if you guys on the call have any questions.